Hello and welcome to this CATIA prismatic machining tutorial. Today we're going to look at how to perform or set up a profiling operation. And this is continuing on the first operation which we did on the part that you see in front of you, which was to face off material from the stock down to the top of the part. So if we look at the part operation, you recall that inside the part operation there's a manufacturing program, and in that manufacturing program there's a tool change in which the facing operation that we created is present. Let's look at the part a little bit to see how we're going to proceed. You can see the stock here in the transparent color and the part showing through it. I'm going to go ahead and hide the stock. And if you look at this part, there are a number of ways one can proceed. I'm going to proceed by performing a profiling operation that's going to machine from the top of the stock, the remaining stock, down to this profile here, which runs around the boundary of the part. So that's going to be done, of course, using an end mill. And the question that one would want to ask oneself is, what size end mill can one use for this? Notice that you have these regions here where the cutter has to move around these circular arcs, so you have to make sure that you have a cutter that is small enough to do this. So one way to check this is to use the measure tool. So I'm going to go down here and I'm going to click on the measure tool, and I'm going to measure this the radius of this arc. So this tells me that it's about 0.44 inches radius. So if I were to use a 3/4 of an inch end mill, I would probably be fine in terms of being able to get in there and remove material. So these are the things that you have to look at before you start moving ahead and planning or defining your operation. So 3/4 end mill will work for this. So let's go ahead and start defining our operation. We want to insert the operation after the facing operation. So I'm going to go ahead here to my machining operations toolbar, and I'm going to pick on the profile contouring tool, and I'm going to insert it after the facing operation. And here is our dialog box, our definition window. You'll see that CATIA assumes that you're going to be using the same tool as the operation you picked on, which is the face mill. Obviously that's not going to be the case, but to proceed, we're going to assume that, or CATIA is going to assume that. Let's go ahead and look at the definition window here. As you recall from the facing operation, this window has a bunch of pickable elements that allow you to define the geometry. Again, I draw your attention to the tabs up here. Remember that the default tab that you start on whenever you define a new operation is the second tab, which is your geometry definition tab, and then you will move to the right and define the other elements that belong to the operation, and then double back across to the first tab. That's the last one you typically do. So let us look at this definition window here, this illustration. There are a couple of things to point out. First of all, you have your bottom, which defines the bottom surface to which the profiling operation is going to machine to. You have the guiding element, which will define the drive surface, which will define the profile along which the cutter will move. You have the top of your part, a top plane, which defines where the cutting tool will first hit material. You have a start relimiting element, and this is typically used when you have a profile that doesn't complete a circuit. Now if you look at this part here, this profile is going to run around the entire boundary and come back to the start point. So there really isn't a beginning element or an end element. So these relimiting elements will not be used in this case. And the other thing you can do is select a fixturing element, but as you can see from, again, this example, we don't have a fixture present. A couple of other things to point out. The bottom here, it says hard. If you click on this, you'll notice that this bottom disappears. And you can use a soft bottom if, for example, you're profiling around a contour where there's no bottom surface for the tool to run on. Again, this is not the case in this part because we have this flat surface that the tool must move on. So we want to make sure that this is a hard bottom. There's also an option to turn the top into a hard top. Right now it's soft, meaning that there's no restriction on the height of the tool. But if we click on this, notice that there's now a option to select a limiting element for the top of the tool. That's actually displaying here. So in this example, it's you're seeing that the cutter is doing an undercut. So that would be a good example of when you would use this. However, in this case, as you can see here, that does not exist, so we're going to make sure that this is a soft top. So let's go ahead and start defining our geometry. What I'm going to do is I'm going to pick the bottom, and then I'm going to pick this plane here to define the bottom. Notice that CATIA automatically selects the guiding element. It uses the boundaries of the face that I selected and picks one of these. In this case, it picked the wrong one. It's actually picking this outer edge here as the guiding element, and that's incorrect. We actually want the inner edge to be the guiding element. So what I'm going to do is I'm going to go ahead here and right click on this and remove all contours. So there's no guide element selected. It turns red again. And what I'm going to do is right click on this, and I'm going to select the guiding elements, or the drive curve, using belt of faces. So I'm going to select this, and then what I'm going to do here is I'm going to pick on a face. You notice here that the face selection dialog box, or toolbar, sorry, pops up. And so I picked this face. In order for me to be able to access some of these tools that are grayed out, I have to pick an adjacent face to define a direction around which the faces are going to span this profile. So I'm going to zoom in a bit, and I'm going to pick this face that is adjacent to the first face. Now you'll see that some of these tools that were grayed out are now pickable. I'm going to use the second tool, which is navigate on faces until a face. So the idea here is that I've defined a direction, and CATIA is going to automatically pick all these other faces. However, I have to tell CATIA how far do I want to navigate. Actually, I want to navigate all the way back around to this face, which is the one that's adjacent on the other side to the first face. So I'm going to pick this tool, and then I'm going to select this face. And if you were looking carefully, you'll see that all the faces around the boundary are now picked all the way back to the first face that I selected. And the guide element now is correctly defined on the inner boundary instead of where it was previously on the outer boundary. So I'm going to hit OK here. Notice now that I have two parts of my definition window green. And the last thing that I'm going to pick is the top plane. And remember that the first operation faced material down to this plane here. So that's where our tool first hits material. So I'm going to select this face, this element in the window, and then I'm going to pick this face here. And now I have pretty much everything that I need to define the geometry of the profiling operation green. Again, as I said, we don't need a fixture, and because it's a complete circuit around the part, we don't need a relimiting element at the start or at the end. Now that we've defined the geometry, let's come back up here to our tabs. So we're going to move over to the third tab, which is our tooling definition. And as I said previously, CATIA is assuming that we're using the face mill, which is incorrect. So we have to change the tool. These buttons up here indicate the different tools that are available. I'm going to go ahead and select an end mill. If you look down here under the resource list, just by doing that, I've added a new tool to the resource list, T2 end mill. So this is going to be tool number 2. Let me change the definition here so that it's a little bit more descriptive of what I'll be using. Recall, we figured out that the tool minimum, or a tool size that would work in this case, is a 3/4 end mill. So I'm going to put in 0.75 to remind me that that's the tool that I'm going to be defining. If you recall from the facing operation, when we defined the facing operation, we had the option to pick these various dimensions within this window here to be able to resize the tool. And again, if you hold on the control button and your middle mouse button, you can zoom in, you can pan around, So you have the ability to move things around, pan in and out, and use this to pick and change the dimensions you want to. The other option to do this is, as you recall, using the More button. So I'm going to go ahead and change some of these dimensions. Recall our diameter is going to be 0.75. I'm going to also change the shank diameter so it matches. And as far as the length of the tool goes, again, you can change these. Maybe 4 inches is a nice, a better number than the previous one. LC is the length of cut. This is the flute length. I'm going to change this to 2 inches. And then the radius, this is the corner radius of the cutter. This is very large. I'm going to reduce this down to, let's say, 20 thousandths. So here is our cutter geometry. Again, the main thing here is our 0.75 diameter. So I'm going to move this over a little bit, and let's look up here. We have a couple of other tabs that we need to look at before we finish the definition of our tool. The first one is technology. So this is where we get to define the number of flutes in our cutter. Right now it's set to 4. That was the default that we use for the, or the value we use for the face mill. Let's go ahead and make this a 3-fluter. Way of rotation, right hand. This is the default. Normally it's right hand, unless there's some reason you want to use a left hand tool, in which case you're rotating counterclockwise instead of clockwise. Machining quality, we leave it as either, so we can rough and finish. Composition, we're going to have a one-piece tool, and we're going to assume that it's made from high-speed steel. And again, this other information down here, which defines the details of the cutting tool, cutting tip geometry, or the flute geometry, angles and so on, you don't really need to set these. They're not really important as far as the toolpath generation goes that we're working on here. So that's the second tab. The third tab is our feeds and speeds, and we have our finishing speeds on top, our roughing speeds on the bottom. I normally set the roughing speeds first, and I normally work with the roughing spindle speed. So I'm going to select this button here to change the grayed out field from here to the one above. So as far as the spindle speed, or the RPM, goes, we have a 3/4 end mill that we want to use for cutting aluminum, high-speed steel. So our formula is 4 times surface feet per minute. We typically use 250 surface feet per minute for aluminum. So that gives us 1,000, and we're dividing that by 0.75. So that gives us about 1,350 RPM. I'm going to just put in 1,500 RPM here for my. I'm going to round it up to a number that's close. So 1,500 turns per minute, or RPM. I'm going to hit the Tab key. Notice that the roughing cutting speed is updated based upon this, using the formula, the exact formula where we use 12 over pi instead of 4. So this is our RPM. Now our roughing feed rate per toot. So I'm going to experiment a little bit with this. I'm going to put in a roughing feed rate per toot of about, let's start off with 4,000 inches per toot. So I'm going to hit the Tab key. Notice here that what happens down here is that the roughing feed rate, which is inches per turn, so this is how far the cutter will advance in a single turn, is calculated, and this is simply the flute number times the feet per toot. So now my feet per minute, my inches per minute, is going to be my feet per turn times my RPM. And if you look at this here, it's probably not quite 20. So maybe I want to bump this up a little bit, maybe to, let's go up to 6 inches per turn. So this here is getting me up, above 20 inches per minute, which is a good feed rate for a 0.75 inch end mill. So this is our roughing speeds and feeds. Let's move up to our finishing. For the finishing, we can, typically the rule of thumb might be to increase your RPM a little bit. So let's go to 2,000 RPM. And our finishing feed rate per toot, we may want to slow it down. So instead of at 0.006 of an inch per turn per toot, we can reduce this down to maybe 4 thousandths. Actually, let's go to 3. So again, if we multiply 2000 by 0.009, we're ending up with 18 inches per minute. That might still be a little bit fast, so let's maybe bump this down to 2 inches per turn per toot. And that gives us 6 thousandths per turn times 2000 RPM, which gives us 12 inches per minute, which is a good feed rate for finishing. So that's kind of how you go about setting your finishing RPM and feed rate, and that's our third tab. Okay, so we've set our speeds and feeds for the tool, and that's our third tab. Now we want to move to the fourth tab, and this allows us to set the feeds and speeds for the operation. So you can override what you have set in the tool, as I've mentioned previously. So let us look at what's written here. We see that our machining feed rate is 27 inches per minute. This was copied in from the tool. It's grayed out. Our finishing RPM is feed rate is 12 inches per minute, and then our roughing speed is 1500 RPM. Also, our approach is set to 8 inches, and if you recall, this is what we set in the facing operation. So CATIA copies over these values from the previous operation. So an approach of 8 inches per minute and a retract of 40 inches per minute, which is pretty good. We can work with that. If I wanted to change the machining feed rate, I would have to deselect this, and then this field becomes editable, so I can change the machining feed rate for roughing as well as for finishing. However, in this case, we're just going to work with the feed rates that were calculated based upon the information we put in the cutting tool. So this looks pretty good, so we're going to continue on to our fifth tab. So for more details on setting approaches and retracts for this macro management tab, please refer to the video that deals specifically with this topic. What I'm going to do here is just quickly set up what I think will be adequate for this particular operation. So in this macro management window, there are a whole set of different approach and retract macros that help the tool approach the material and move away from it, when one is performing different steps in the operation. Down here is a window that allows you to define for the different options that you select here what the approach move or retract move would look like. So this window here is just like the other windows. The image here, you can zoom in and pan and move things around. These buttons on the bottom here allow you to define different moves to build your approach and retract steps. So yeah, you just have to construct your tool path for your approach using these buttons here. There are a few options of canned approaches and retracts. So for example, if I click on this flyout here and click on circular horizontal axial, this here shows me one example of a canned or preset approach move that I can add to any one of these approach or retract macros. However, I'm going to start off by using the build by user option. Actually, let's start with none, so I don't have any operations or any moves present. And then I'm going to move over to build by user, which is going to put up these buttons again so I can start constructing the approach move as I need it. So let's look at these options here and see which ones we want to set. We do want to set the initial approach. This is the move that the tool makes, probably from a tool change or from a previous operation, to position the tool so that it approaches the very first cut in this operation. And this is the retract at the end of the operation. So I want to set these. So what I'm going to do first of all is activate both of these by right-clicking, highlighting, right-clicking, and activating. Let's go to the approach. What I would like to do is make sure that I switch the tool into approach before it hits material. Now for this profiling operation, I'm going to use a 0.2 depth of cut per pass. So in order for me to make sure that the tool is in approach mode as it enters material, my approach distance has to be at least 0.2. I probably want it to be a little bit larger. I'm going to use 0.3 as my approach depth. So what I'm going to do is I'm going to come down here to the toolbar, and I'm going to go ahead and pick on Add Axial Motion. So what is done here is an axial motion, approach motion is added. The length of the approach motion is about 0.4. I'm going to double click on this, and I'm going to change it to 0.3. So I now have an approach move of 0.3. So the tool is going to switch over to the approach feed rate, 0.3 above the depth that it's going to be cutting at. And again, the approach feed rate, I can see that if I go back to the fourth tab, that's 8 inches per minute. So it's given that the depth of cut, the amount of material that is present is going to be 0.2. As we drop downwards, it means that there's going to be 100 thousandths before the tool hits material, and then it's going to be moving into the material at 8 inches per minute. This is a plunge move, or it could be off the part, but in some cases it will be a plunge move straight into material. The retract move, I'm going to, right now there is a tool path retract that's included. I'm going to remove this. The way you remove moves that are already present is by coming to the toolbar and moving down to this button here, which is to remove the motions. So for the retract move, I'm going to do the same. I'm going to select the axial motion now that I've deleted the previous motion. I'm going to select axial, and I'm going to set this up to 0.3. Now, as the tool gets deeper and deeper into the part, that 0.3 is going to, the tool isn't going to lift far enough up. If it had to reposition to another part of the profile, it will move, it will crash into the part. So that's why we want to set our clearance move. What the clearance move does is it before you get to an approach move, it tells the tool how high it needs to lift before it gets to the beginning of the approach move. So the tool will hit the clearance plane, whatever we select as the clearance plane, and then wrap it down to the start of the approach move. It's probably a good idea to set this to the safety plane that is defined in your part operation. Remember, we set the safety plane as one of the parameters in the part operation. So I'm going to just activate the safety plane. So now it means that there's going to be a rapid move from the safety plane to the start of the approach, which is going to be 100 thousandths above material. Switch to feed mode, and then it's going to feed downwards 0.3 till it gets to the level of the tool path where the cut's going to take place. So now that the clearance is set, if we move down further in this list, the linking, retract, and approach, we're not going to be linking between profiling operations here, so we can ignore these. The next ones down are the return in a level, retract, return in a level, approach. So more than likely, as we machine this profile, we're going to have to use more than one pass. Those passes are going to be on the same level, and it's possible that the tool is going to have to lift up to reposition from one pass to the other. So I'm going to activate these. So I'm going to activate, and notice that both of these get activated when I click and activate the retract. I'm going to do the same thing that I did for the initial approach and retract. I'm going to use an axial move. I'm going to set that to 0.3. Make sure I have 100 thousandths before I hit material. And I'm going to do the same thing for the retract. Moving downwards to the next pair. The next pair is return finish pass retract, return finish pass approach. We would want to set these if we have a finish pass as part of our profiling operation. I'm going to set these because more than likely I'm going to include a finishing pass. So let me activate these. Again, both get activated. And I'm going to do the same thing as before, set an axial motion, again making sure that it is 0.3. Now it doesn't have to be 0.3 in this case, because normally for a finishing operation you probably don't have a lot of material left. You probably have maybe 10 thousandths, but to be on the safe side I'm going to set this to 0.3 just as I did for the other approach macros. And then the same thing for the, sorry, that was the retract. Now I'm going to set the approach. I'm going to use an axial move, and set that to 0.3. And then the last pair has to do with moving between levels. So this profiling operation is going to probably take 4 or 5 levels depending on the depth of cut we need to get to. And then as the cutter positions from one level to the next, these two macros here control how the tool approaches the next level and then retracts from it. So I'm going to activate these just as I activated the others. And then I'm going to, again, just use an axial move up of 0.3, both for the retract and for the approach. So again, that should be sufficient if I am removing no more than 200 thousandths per pass. The tool will lift up and it will approach, and there will be 100 thousandths before it hits material. Again, the approach feed rate will be based upon what I said in the 4th tab, which is 8 inches per minute. So that's the 5th tab. Again, there's a lot more to setting approaches and retracts. As you can see from this toolbar, there are interesting things one can do. For example, one can have helical motions and so on, as one can see here. And as I said previously, you can look at the video that deals specifically with this topic if you want more information about setting approaches and retracts. Okay, so now that we've done with our approaches and retracts, what we're going to do now is move all the way over to the very first tab. And I'm going to click on this. This is where we get to set our toolpath strategy. So things like our step over, our axial depth of cut, how many passes or how many levels we're going to cut, whether we set a finishing pass, what's the depth of the finishing pass, and so on. So there are 4 tabs here. Actually, the only ones we need to set or play around with in this case are the first 3. The very first thing we want to look at is the toolpath style. This is how the tool moves around. This flyout here indicates the different options that one has. Zigzag, meaning the tool moves back and forth. One way, meaning that the tool moves in one direction only as it moves around the profile. And then helix, so the tool moves with a helix as it descends from one level to the other. I'm going to just use, in this case, one way, so the cutter moves around the profile in one direction. This way we can control whether the cutter is in climb mode or conventional mode, and typically that gives a better finish. So as you can see here, you have the option to set that mode, climb or conventional. By setting it to climb, CATIA will automatically, given that you want the cutter is rotating clockwise, it will pick the direction of motion to ensure that the tool is climbing. Similarly, if you switch it to conventional, it will set the tool to conventional, the direction to give conventional cutting, given that the cutter is rotating in a clockwise direction. Machining tolerance, this is if you are cutting curves. In this case here, probably most of the toolpaths are going to be done using circular interpolation, so one should get an accurate cut based upon the hardware of the machine and not an approximation. Leave this at 4 thousandths anyway, but I don't think it'll be used in this case. The type of contour, this refers to how the tool moves around sharp corners. I would leave that to circular. It means that CATIA throws in a circular move around corners, so the tool rolls around the corner. Helps to make sure that you end up with puts a little bit of a radius actually on the corner, which is not a bad thing. Do we want to close the toolpath? Again, click on the question mark. Shows you what that means. Yes, we want to close the toolpath. Percentage overlap, this question mark here, if you want the tool to move past the start point a bit, yes, I think that's a good idea. If you remember, sometimes you can leave cusps if you try to stop the tool exactly at the same starting point. So let's have a 50% overlap. And then the rest of these options here you don't need to worry about. So this sets our machining toolpath style, the first tab here. The second tab is our step over. So we have different ways in which we can control step over. The sequencing is the very first option, and again the question mark helps you understand what the different sequencing options are meant to do. So radial first means that the tool removes material from the outside in first before it descends to the next level. So as you can see here from the numbers, 1, 2, then it comes back to 3, 4, 5, 6. That's how the material is removed. There's also axial first, meaning that the tool will move downwards. So 1, 2, 3, then lift up 4, 5, 6. We're going to use the radial first option. And then the radial strategy, the distance between paths, 1.8, so that's the step over between the paths, or the number of paths that we're going to use, and the number of paths that we're going to use. So remember, we're working with a 0.75 diameter cutter, so the distance between paths has to be less than that. I'm going to set this to 0.7 inches, so there is 50 thousandths overlap. The number of paths, this is maybe something that we're going to have to play around with. Looking at this geometry here, I'm suspecting that 2 paths would probably be enough. So I'm going to go ahead and increase it to 2, but it may be that a third pass is needed, maybe in this region here, in which case we'd have to come back in and add a third pass by stepping this up. So overhang for rework areas, leave that at 50. So this is the sequencing and the radial strategy. The axial strategy, we can define it as being the number of levels. However, often it's better to use the maximum depth of cut, since given our cutter, we typically have that constraint. So I'm going to use that option. And again, the question mark puts a picture up that describes this. Our maximum depth of cut for a 3/4 inch end mill would be 0.2. So I'm going to type in 0.2, hit the tab button, and then CATIA automatically calculates the number of levels that are needed to move from this top surface here to the bottom surface. So 7 levels are needed. The other options on this tab you don't have to worry about for this operation. So again, the step over, we need to set our sequencing, our radial strategy, and then our axial strategy, which controls the number of levels and the depth of cut. Finally, the third tab here is for finishing. Right now we have no finishing pass, and again the question mark helps describe this. There are a bunch of options in here depending on how you want to finish. You can side finish the last level, and again clicking on this with the picture selected shows what this means. It means that we don't have any finishing operation or material on the bottom. We don't finish the bottom, but we do finish the side at the last level, meaning when the cutter is down to depth, it moves in and removes material, depending on how much you set. We could side finish each level, meaning that there is a finishing pass at each level as the tool descends downwards. We can finish the bottom only, so if we don't want to finish the side but want to finish the bottom, we have that option too. We can side finish at each level and bottom, so in this case we're side finishing at each depth, at each pass, and then finally at the bottom we clean up the surface. Or we could side finish at last level and bottom. So in this case, let's keep it simple and just side finish at the last level, in which case we're going to set our side finish distance here. Let's say we want to leave 10 thousandths for a finishing pass on the side. Now the bottom thickness on side finish, we're going to leave that to 0 because we want to finish right down to the bottom surface. Okay, so this is the last tab, the finishing operation. We've also completed all our tabs up here on the top, so we should now be ready to generate our toolpad. Okay, to generate the toolpad, I'm going to move down to the bottom right hand button on the window. It says toolpad replay. I'm going to click on the button. CATIA runs through and generates the toolpaths for us. So here are our toolpaths. A couple of things again to notice. Green means cutting, red means rapid, yellow are our approach moves, blue are our retract moves, and if you look closely you'll see there's a cyan color which indicates a finishing pass. We can rewind or go to the start of the toolpath. Make sure you're in continuous display mode here, which is the very first tool on the set of flyouts, and then we can hit forward replay, and we can see the tool moving around, executing the tool pass. You can see the repositioning moves here as the tool moves from one pass to the other, as well as change depth. So I'm going to pause this. I'm going to rewind it, and I'm going to switch this mode from continuous replay of toolpath to plane by plane replay of toolpath. This can show you a little bit better what's happening as the tool moves from one pass to another, as well as it moves from one level to another. So I'm going to click the forward replay button. So what I see here is this is the initial approach or rapid from tool change, more than likely. The tool hits the clearance plane, which is 200 thousandths above the top of the initial stock. It then rapids downwards until it gets to 300 thousandths above the cut depth. And it's 300 thousandths because that's what we set for our approach move. So if we look a little bit more edge on, we can see that the tool is stopping, because remember we've faced off material to the top of the surface here, that the tool is stopping 100 thousandths above, switching over to feed, that's 8 inches per minute, and then plunging into the material at 8 inches per minute. And then once it's down to depth, it starts cutting, which is the green pass. So I'm going to click the forward replay again, and this will move me all the way around on that pass. Right now I'm cutting the outer pass, because remember we set 2 passes. So this is the outer pass, as you can see here. So now I've finished the outer pass, and the tool is going to reposition to cut the inner pass. So what we have here is a retract move, 0.3. Then the tool switches over to a rapid move. So retract is at 40 inches per minute, rapid is at the rapid rate of the machine, up to the clearance plane. And again, if I go to edge on, you can see that a little bit more clearly, that the height of this rapid move is at the safety plane actually that we set for the machine. The tool rapids over to the start of the inner pass. It rapids down till it gets to 300 thousandths above, and that's where the approach move starts. Tool approaches, and then it starts cutting the inner pass, as you can see here. When it gets back to the start point of the inner pass, what it's going to do now is reposition to the next level, because it's cut material for the first level. So the next play forward will show the tool. Let's see if we get this properly oriented so you can see this. It's a little bit crooked, but I think you get the idea here. You can see that the tool is retracting upwards, switching to rapid mode to get up the clearance or the safety plane. Rapids down. Notice now that I'm descending, because the approach move now is dropping down to the next level, 300 thousandths, and now we're at the next level, and the tool starts cutting that. So that's why it's important that the approach move is greater than the depth of cut, so that the tool never slams into material with that rapid clearance move. We can also, of course, do our material simulation. So I'm going to go to use my view options. I'm going to go to isometric view. I'm going to zoom out a little bit so I can fill the screen. And I'm going to come down here to my second set of tools. Make sure I'm using full video option. And then I'm going to switch this mode back to continuous. It's not going to allow you to do material removal plane by plane. And I'm going to run it forward. So there's the facing. There is the profiling. I'm going to pause it for a second, and then I'm going to actually try and stop it. Yeah, here. So you can kind of see the way that what's happening here. There are 2 passes, if you recall. So you can see what the outer pass is doing. It's not taking a lot of material, and I deliberately set the overlap to start off with to make this point. That outer toolpad is very inefficient, because you are cutting a lot of air in these regions here where it's not removing material. Also, the cutter is taking a lot of material on the inner pass, so it's almost full engagement. So one could, since one is forced to do 2 passes, one might as well redistribute the or change the step over so that the cutting is more evenly distributed between the inner and outer pass. So we'll do that in a second, but I just wanted to point that out to you. Let's just continue this through, and we're all the way down to our depth, final depth. So let's make that change. Obviously from the simulation we can better distribute our material removal between those two passes. So what I'm going to do is I'm going to come over to my step over, and let's say instead of 0.7, let's reduce it down to 0.375. I'll regenerate our tool paths. Let's go into our video or material removal mode. Let's run. So as you can see here, the tool is actually now cutting an outer pass and then stepping inwards and cutting an inner pass. And there's a much better distribution of the amount of material that's being removed between the inner and outer passes versus the previous case. Now one could probably speed the feed rate up. So one might be saying to oneself that maybe the option of taking all the material, you use a slower feed rate. That's true. But in this case, one could possibly increase the feed rate so that one can remove the material faster because there's less width of cut given the redistribution of the step over, or the change of step over. So let's finish this up. There we go. We finished our profiling operation. So I'm going to hit OK here. Looks good. So what I'm going to do is hit the OK button. Remember to hit the OK button. Don't hit cancel. Otherwise you just lost all your work. Hit OK. And then if we look briefly at our tree, we'll see that we now have our profiling operation that's been added to the tree. CATIA has now inserted a new tool change because we're using a new end mill, or a new tool, which is an end mill. So there has to be a tool change after the facing operation to bring this tool up so that the profiling operation can be executed. And we may well use this end mill to do some more operations, and those operations would end up within the same tool change if that's the case. So that's how you would set up a profiling operation using the prismatic machining workbench in CATIA.